Hello everyone, welcome to a pilot study on video object detection,
My name is Abhishek Rajora.
and I am Abu Shahid. Let us begin. Video object detection is a fundamental task in computer vision that involves identifying localizing objects of interest in videos. Unlike image based object detection, video detection requires the consideration of temporal information and the ability to track objects across the frames. It plays a vital role in various applications, including video surveillance, action recognition, etc. However, video object detection poses unique challenges such as motion blur, occlusion, changes in lighting conditions, and complex object interactions. We will be briefly going through the dataset used, the literature review, implementation, and finally the analysis. The dataset we used was a subset of ILSRC 2016 because it is a very standard dataset and all the literature we went through reported the results in one of the versions of the dataset only. The dataset is however not available publicly and therefore a subset of it was made online and used. The dataset stats can be seen in the table. In our literature review, we went through the following papers.
For mask RCN, it is a meta algorithm which is designed to be simple and intuitive. It is based on fast RCN and FCN with parallel heads to match a mask object at each frame. So basically, we maintain it is a two-stage detector, and we used ROI align to maintain spatial information instead of ROI pooling. And it was basically the main algorithm for instant segmentation, but we see that it has also improved results for object detection. The second model is RetinaNet, and it is implemented with the backbone of feature pyramid network on top of a feed-forward ResNet network. Feature pyramid network consists of multiple branches with different spatial resolutions that allows us to detect objects of multiple scale feature, and the backbones used here were the ResNet architecture used here were ResNet 50 and ResNet 101. It also includes the focal loss, which basically describes us about the class imbalance. And the focal loss here deals with the problems of that hard examples are hard to distinguish. So basically, we assign weights to downsample the easy examples.
Temporal ROI. Temporal ROI extract most of the similar ROI features from support frames for target frame proposal based on feature similarity, implicitly incorporating temporal information. A temporal attention mechanism is employed to aggregate these ROI features, giving more importance to clear objects instances. The proposed operator not only improves performance in video object detection but also has potential applications in other video tasks such as video instance segmentation and etc.
Now for Boss Mask, it is incorporated using key ideas from the two-stage detector model called Mask RCNN. And in detection phase, it is equipped with a Boss Mask head at the bottom, and RPN. The RPN generates candidate object regions, and the Boss Mask and Mask head that were integrated at the bottom are used to classify the objects in the region of interest.
So most of these approaches are two stages. Traditional two-stage approaches suffer from low speed due to large number of low confidence region candidates. To overcome this limitation, the authors introduced a two-stage pipeline where the first stage involves prediction and discarding regions with low confidence, while the second stage focuses on region level refinement through temporal aggregation. Feature selection module is introduced to select high quality candidates from feature maps of the detection head. This module picks top prediction based on confidence scores, applies non-maximal suppression to reduce redundancy, and collects the features of those predictions for further refinement.
Now we move on to the transformer-based approach, that is VSTAM, and it is based on the sparse attention mechanism, and it keeps track of the past M frames which are relevant, and it keeps long-distance relevance through the help of external memory. It also adaptively stores the feature of the most vital frames in the external memory. And the concept used here are random and positional attention mechanism. The positional attention mechanism is basically a correlation between the consecutive frames, which helps in finding out the occlusions and helps in detection of these objects. And for the random, It is a sparse attention mechanism which is used for alignment and object tracking.
Finally, let's look at TransVOD. TransVOD is a framework that consists of a shared scene in Backbone for feature extraction from multiple frames. It utilizes spatial transformer encoders to create feature memories which are then combined and pressed through temporal deformable transformer encoder. Spatial transformer decoder is responsible for decoding spatial object queries. A temporal query encoder models relation between different queries and aggregates them to enhance the object query of the current frame. Now let's look at the metrics that we used in our study. The metrics that we used were IOU and mean average precision because of their simplicity and because of how easily they are cited everywhere.
Now for the analysis, we will look at the ROI align versus ROI pool. And we observed that the ROI align has better MAP in most of the cases, in basically all the cases, because in ROI align the spatial features are preserved, and in ROI align they are distracted because the ROI pool pool works like they assign fixed size bins and we then do the max pooling. And in ROI align we use bilinear interpolation to sample the feature map at a set of regularly spaced points. So then we apply the max pooling over it, so by preserving the spatial information. Now looking at the focal loss with varying alpha and gamma values. So this is based on the resonance structure, and alpha values basically represent the weighing factor, which basically implies the importance of positive and negative samples. And gamma values are called focusing parameter, and these basically downsamples the easy examples. So their loss has minimum weights, and the classification due to wrong examples are downsampled and hard examples are upsampled. Now finally, we applied the box mask on RetinaNet object detection, and we observed that it was able to perform quite well and it has increased its accuracy. And using box mask, we were able to add number of parameters, and it had become and it still fails under occlusion and different illumination changes, but it is not completely like transformers. Transformers are on next level, but it is quite a unique technique to apply box mask with it. Now let's switch to demo. So we see that we have applied the object detection model, the RetinaNet object detection model with box mask. So we will see in real time how it performs on this video described here. For this, we'll run this GUI.py file, which basically contains subplots of all the frames. So here we see that the bikers are getting detected, and some of the times we see that there is also a detection of backpack, which is often occluded in it, which are recognized by the transformer based approaches. And it is not the best approach, but it has quite significant increase in its accuracy. So we will stop this. Finally, we have done a real-time video analysis of our videos. For that, we use the camdetect.py file to generate video, and then we just see how this perform on our object detection. We see that the cell phones are getting detected, and in some of the cases, it is not able to actually recognize it quite well. And we see that the headphones are here behind my neck, so they are actually occluded and not able to identify behind my neck. So, and finally we will move to the examples. This is the first example. This is based on the RetinaNet model, the RetinaNet base model, and it was actually a outlier which RetinaNet was not able to detect. So by performing box mask, we see that we are able to detect the bounding boxes quite well. And this basically happens because of the number of increased parameters and the efficient computing. So thank you. That was it.
Thank you.